Hey, good morning.
Morning, sir.
And okay, there. I think the screen is visible. Yes, it is. Chat box ready. Okay, so we began by introducing the concept of the first half of Module 2, which is analyzing the 3D nature of our molecules. And I gave lots of different cool 3D examples. I mean, using my models. And one of the models that I showed you guys was that of the form of parang this particular molecule here. It's just everything singly bonded. And we were able to show that this molecule had two distinct forms, diba? One were in the large groups or the highlighted groups like this red and the blue were on the same side of the molecule. And then we rotated it, remember? And then we showed you another form of the same molecule. Now, unlike the other ones that we did during the demonstration, where I had to physically break bonds, diba, and transfer atoms, we said that because I only exploited the nature of the molecule itself, I only exploited the fact that it had sigma bonds that can rotate, that we did not change the chemical nature of this molecule per se, or identity. But we did notice that there are two particular forms that were of noteworthy of ano diba, parang of noteworthy rather. Yeah. So we had a form wherein the functional groups red and blue were on the same side, and then we had the form wherein the functional groups red and blue were on opposite sides. And I asked you guys if you would think they would have the same or different energy level, and I think yeah, we all came to the conclusion that they did have different energy levels or stabilities. And so that's what we're going to look at today. We're going to look at analyzing how the different forms of a molecule arise from simply rotating bonds. So again, sigma bonds on their own are perfectly able to rotate. So plain sigma bonds can rotate, so you can twist it. It's obvious here, or you can just twist it like a doorknob like that for atoms, diba? Now this then means that there will come or there might arise different forms within a given molecule. Now these different forms that arise are called conformers. So they're not called stereoisomers per se. Some books will consider stereoisomers as conformers or other conformers as stereoisomers. But for my course, I do not want to confuse the two. So we will just call them conformers, or other books will call it conformations. So they mean the same thing, conformations or conformers. They simply mean the same form of the same molecule, just different rotational forms. Okay, so it's like you wiggled or jiggled the molecule, but you didn't break any bonds. So, how do we systematically study conformers or conformations in molecules? We do so by using a tool called the Newman projection. Okay, and a Newman projection is pretty straightforward and simple. It's just a way of drawing a molecule or analyzing it through a certain point of view or perspective. It's a form of perspective drawing. Okay. So look at this one on my screen. So on my camera, I have this molecule again. I have two carbons. One carbon has a blue functional group, one has a red functional group. Now, I'm going to point my molecule towards the camera in this particular fashion. So yan, kita nyo? So now, the carbon in the front is perfectly aligned to another carbon in the back. So this one. The carbon in the front is the one that has this blue functional group, okay? The carbon in the back has the red functional group. Clear so far to everyone? Okay, now, the carbon in the front, we draw as a thick dot. So I'm gonna draw it here, a thick dot on my screen. Okay, now, on the carbon to the front, what do you guys see pointing out of it? It has this blue going up, right? And these two hydrogens going side to side. So let's go ahead and draw that. So we'll have carbon in the front, thick dot. I'll translate it to blue. I'll put this blue functional group here. So I'll write it as B. Okay. And then going side to side, but a little bit downwards, so left and right downwards, are your white hydrogen atoms. So, yeah. Clear so far? Kaya? Thumbs up, everyone who follows. So try to do this on your own as well. Now, sir, what about the carbon in the back? Right now, it's invisible because it's perfectly eclipsed, or kita nyo, it's perfectly hidden by the carbon in the front. So how do we draw the carbon in the back? So in order to escape that, the carbon in the back is drawn as a larger circle that's hollow. So that red hollow circle actually represents this carbon in the back. Clear so far? And we will then draw whatever's attached to that carbon in the back. Now you have to remember that you're supposed to draw it bonded to only that carbon in the back. So let's pretend we have this red functional group that's also going upwards right behind the blue one. You're not going to draw a bond like that. So that's wrong. Remember that the red functional group is bonded only to the back carbon. So starting from the back carbon, you will draw that bond to the red group. Clear? And then you will draw your hydrogens as well. So you might have to put it a little bit ajar because you don't want to draw or write things in front of or right behind that stuff that you drew because it defeats the purpose of analyzing the structure. So okay lang kung medyo naka-off silang ganyan, that's fine. That still means that they are perfectly aligned like this. Okay? So yan siya. This is called the Newman projection. Okay? Now, depending on the conformation of your molecule, meaning how further along you are at rotating your molecule, your Newman projection can also rotate or change its forms. Okay? So you can imagine we can move this one, these groups that are red, we can move them that direction. The groups in blue, we can move them in another direction or even in the same direction, etc. So a Newman projection, it's like a double Ferris wheel. We can rotate either the front or the back, either way. Okay, now, when we translate to a Newman projection, we can actually clearly see the different conformations of our molecule. And these different conformations will in turn have different levels of stability. So some forms will be high energy unstable forms, and some forms will be lower energy, more stable forms. Let's go back to this form of that we drew a while ago, diba? We had this particular version here, wherein you had your groups all aligned. This Newman projection that we drew a while ago, so this is for this is for ethane. This is called an eclipsed conformation. Eclipsed conformation. So in an eclipsed conformation, literally, but we mean eclipsed like the moon literally blocking the sun. Diba? Everything's eclipsed or perfectly aligned. Okay. Eclipsed conformations are high energy or unstable because you have the electron clouds of all these groups that are aligned. So like this blue and this red, for instance, okay? These are the closest that the red and the blue will be. Any others that they'll go further away from each other. So this is the closest they'll be. And if you can imagine, the blue and the red, diba, these are atoms, and atoms are orbited by electrons. So you can imagine the surface of this blue and this red atom, both negative and therefore repelling each other. And that kind of repulsion, that brings tension within the molecule, that brings instability. Okay. Furthermore, aside from that repulsion or the repelling of the negative clouds of each atom, you have to remember that these are ball and stick models and they don't represent reality. In reality, the electrons are like bigger, fluffier clouds around everything. So ganyan. So it's like my fists. Okay? And so with that, imagining it everything more bulky and bigger and fluffier, you can see that the electron clouds of each atom are trying to take up the same space. If it's in this eclipsed form, they're trying to take up the same space. This phenomenon is called steric crowding, or most books actually call it steric hindrance. So they're hindering each other, they're blocking each other, trying to take each other's space. So steric hindrance, or yun nga, the electron clouds are crowding each other, crowded. So steric crowding, they mean the same thing. Okay. And so repulsion and steric hindrance cause this particular eclipsed form to be very high energy. Now, what if you rotate it? Let's rotate the back carbon. What happens now? So the groups are now far away from each other. Okay. In fact, in this particular form, all the groups are the furthest away from each other as they can be. With that, we know that this is now the most stable form of the molecule that there can be. So front, back, front, back, front, back. So I'm literally I'm going back and forth. This particular form of alternating front and back, this is called the staggered form. And the staggered form is the most stable or the lowest energy form because we avoid all of that repulsion, we avoid that crowding, that steric crowding. There is still some, it's still there, it's inescapable, everything's covered in electrons, but we've minimized it. Okay. In fact, aside from just the perfectly eclipsed and the perfectly staggered, if you notice, again, diba, you can rotate it. So there will be forms where it's a little bit off, it's a little bit off, it's a little bit off, and then it's staggered. And then staggered becoming more and more eclipsed until it's perfectly eclipsed. And then eclipsed becoming more and more staggered until it's staggered. So all of these particular rotations or will have a certain level of energy for your molecule. And so in fact, if you graph everything continuously, you'll end up with the sine wave. Kadire, math, sorry. But like, yeah. So ito yung kanyang giging energy graph. Siyempre, in chemistry, we're only going to be interested in the highest possible energy or the least stable forms. And we're also just going to be interested in the lowest energy or most stable forms. So these are the forms that matter. These are the eclipsed conformations up there, not the not so nice high energy forms. These are the very stable staggered forms below. Okay, so dyan tayo mas concerned sa eclipsed and sa staggereds. Okay, needless to say, again, things can exist between those. Now, let's go ahead and now analyze a larger molecule. Let's look at butane. When analyzing larger molecules now, so it's we don't have to just analyze 2 carbon molecules. When analyzing larger molecules that have more carbons, we will always designate what point of view or what perspective we're going to use. So for instance, in this particular analysis, we're going to look at butane, which is a 4-carbon molecule, but we're going to view along the point of view or perspective of citing along carbon 2 to carbon 3. What does that mean? So if we have our butane, for instance, we have carbon 1, carbon 2, carbon 3, carbon 4. Citing along carbon 2 to carbon 3 means that carbon 2 will be our front carbon, the thick dot, and then carbon 3 will be our hollow circle. So this is going to be us. So that's us. Okay, this is our shades. We're going to be looking from 2 going to 3. Okay. Kita? We're going to look from 2 to 3. So carbon 2 is that dot. This is it. Carbon 2. And then carbon 3 is the hollow circle behind it. Going up from carbon 2. Going up. What carbon is that? It's a CH3. That's carbon number 1. So that CH3 up there is carbon 1. Diba? And then aside from that, going side to side on carbon 2 as well. What are these? In blue. Going downwards to the right and downwards to the left. Those are your hydrogens in blue. Diba? Kita? Does everyone follow so far the perspective? Okay. Carbon 3. Carbon 3. Here in the back is this circle. Going downwards from carbon 3. It's this CH3, which we also know as carbon number 4. And then going upwards a little bit to the right and to the left are your hydrogens. Okay. So this particular form of butane that we drew, is this an eclipsed form or a staggered form of butane? Type in the chat box so I can check. So this particular form that we drew, is this our staggered form or is this the eclipsed form? Okay, I'm seeing 1, 2, 3. So correct. This is the staggered conformation of butane. Now, this particular form of staggered, okay, has a special classification. Okay. It's not just any form of staggered butane. If you look at the carbon in the front and the carbon in the back, they each have a key group, meaning or the largest group on them. So the carbon in the front has this large CH3 group. Carbon in the back also has this large CH3 group. If you notice that these two key groups on each of the carbons in the front and the back are completely 180 degrees in terms of away from each other, in terms of the dihedral angle or the angle in the Newman projection. So the largest groups are the furthest away they could be from each other. This is called your anti-staggered form. So we have the conformations, we have eclipsed, we have staggered. And then under staggered, you have your anti-staggered form. Okay, so that's like in the hierarchy of it. Okay. You rotate the bond a little bit, you end up with this eclipsed form, and then clear. Okay. So yeah, anti-staggered. Two largest groups, 180 degrees away from each other in your Newton projection. This is also the most stable form. Okay. Now, going back to our Newton projection, if you rotate our butane just a little bit, you'll end up with this particular form. It's still staggered. Kita nyo? It's still staggered, but the two largest groups are near each other. They're not eclipsed, but they're near each other. So they're right beside each other on the Newman projection. So this is called the gauche staggered. So again, under staggered, this is a particular form of staggered called the gauche staggered. Now, between the gauche staggered and the anti-staggered, which has the higher energy level? The chat box. Which is the higher energy level, which means it's slightly less stable or unfavored. The gauche staggered or the anti-staggered? So si gauche, tama. In fact, yun nga, naka-state na dito that there is some steric strain between the groups being gauche staggered to each other. So it's staggered, but it's not the best form of staggered. It's not very stable. Yan. Parang sinabi mo, kumari, si red and si blue. Diba? Parang sabi mo, gosh, ayoko sa'yo. Usog ka nga. Ganyan, okay? So they repel each other. Di sila happy together. So yeah, gosh staggered. Okay. Steric strain. Okay na yan. Okay, so to. When we have more complex molecules, their sine wave or their energy level graph becomes more complex. So you won't have the even sine wave that's like everything the same at the top and everything the same at the bottom. So napansin nyo dito, nag-iiba-iba yung levels. So at the very base of the graph, you have these particular places here. They're the lowest point or the most stable parts. And these represent the anti-staggered forms of your molecule. So yun na nasa anti-staggered form. Okay, so from anti-staggered, it becomes eclipsed. And then it stabilizes, but notice this form here. It's stable, but it's not as stable as your anti-staggered. So what form do you think this relates to? Diba? If you look at the graph or if you look at the structure of the Newman projection, this is when the two large groups are staggered but near each other, also known as the gauche staggered. So ito yung mga gauche staggered. Okay? So eclipsed. Now, under eclipse, there's only one special form, okay? The super eclipsed form. And that super eclipsed form is when you have your largest two groups perfectly eclipsed to each other. So what dito, the red and the blue are perfectly eclipsed to each other, front and back. Or in this case, the two CH3 groups are eclipsed to each other. This is called the syn eclipsed. Okay, the syn eclipsed is the highest energy form of a molecule. The two largest groups are perfectly aligned to each other. Syn. It's a sin. It's evil. It's bad. It's unstable. Okay. Syn. Yan. Syn really means same side, by the way. Okay. SYN. Now, when molecule structures become even more complex, you can't just visualize it on your own. Because kunwari, you'll have other groups aside from hydrogens and other parts of the carbon. So, sir, how do we find out if it's the most stable or if it's the least stable form of a molecule? You'll have to use energy cost tables, and they're long tables, and in these tables they will tell you the energy cost of having certain interactions. Like kunwari, if you have a Newman projection and then you have two hydrogens eclipsed, you'll count that as 4 kilojoules per mole for that molecule. And then if a hydrogen and a methyl group, for instance, is eclipsed, that will cost you 6. Or if you have two CH3 groups that are gauche staggered from each other, that will cost you 3.8. Or if you have two CH3 groups eclipse together, that will cost you 11 kilojoules per mole. So notice, bigger groups interacting will cost more energy. So the bulkier or bigger a certain group is, the more it will cost energy of will give more energy cost if it's going to be near or blocking other groups or interacting with other groups. So yun. The table goes on. Syempre, it's not just hydrogens and methyl groups that exist. You'll have other functional groups as well. Okay. So, but don't worry, I won't make you guys graph anything. But do note that if you are confused or lost on how or which form is more stable than the other, then please look for these tables. Okay, and then you can then start adding up the energy levels or energy costs and then determine which is higher energy or lower energy. Okay. Fun fact, notice if we draw alkanes, we always draw in zigzag. Diba? Parang pag hexane, ganyan. Or to decanata. Why do we always draw in zigzag? Simple. If you draw in zigzag, you're actually drawing the most stable form of a chain. If you translate your zigzag skeletal structure into the one with the dashes and wedges, and then translate that into ball and stick, you can see that at any two carbons, so yan, dot and circle, that's us, it'll always be anti-staggered. So that's the beauty of drawing in straight chain, in those zigzag lines. You're always drawing the anti-staggered form of all the molecules. So I want you to convince yourself or try to visualize it. Try to create your own Newman projections for this. It might pop up in your exams. I don't know. Okay, so there. Now, to end this first part of our session, let's do a worked example. This is the kind of analysis that you'll be doing for your exams. No? So in this particular item, you're asked to cite along carbon 1 and carbon 2 of 1-chloropropane. And then draw the Newman projections of the most stable and the least stable of its conformations. So how do we go about this problem here? First things first, you have to translate the IUPAC name into a structure. So 1-chloropropane. Parent chain, propane means how many carbons? Chat box, 3. Tama. 1, 2, 3. Okay. 1-chloropropane means on carbon 1, we will put a chlorine. So can I do this? No. Do I? Bakit no?
Sir, can you hear me?
Yeah, I can hear you nice and clearly.
Ayan. Pag nilagay yung chlorine dyan, magiging dalawa na lang yung carbon.
Exactly. Okay. So I noticed this a lot. So please be very careful. When you're gonna add the functional group, add a bond to that carbon first before you add the functional group. Okay? So kasi pag ginawa nyo na kaagad dyan, nawawala yung particular group na yun. So this is carbon 1, 2. This is 3. Gusto nyo ng 1-chloro. So from 1, you'll add something and then you can add the chloro. Para alam nyo nandun pa rin yung carbon. So I know it seems, I just have to point it out because a lot of students have disappearing carbons when they work, and that invalidates your entire answer already if the molecule itself is wrong. So make sure you do that. Okay. Next, sir, this is just still a flat drawing. I still can't visualize this in 3 dimensions. Well, you have several options. If you have one of these molecular modeling kits at home, you can literally build the molecule. So you build a 3-carbon chain, add chlorine to one end. You'll have a 3-dimensional model and you can visualize it on your own. No? Or if you downloaded the apps that I asked everyone to download, diba? We have now an app called Model AR or Model R, and you can literally 3D model in your iPad or your iPhone or whatever this molecule. So create a 3-carbon chain, add the chlorine, and then you can really swipe and visualize it in 3D and try to come up with and try to view it along carbon 1 and 2. But what if we only are stuck with pen and paper, and you want to work fastly, you don't want to build things and whatever in the middle of an exam? Okay, all we need to do is try to interpret our flat drawing into 3 dimensions using our drawing tricks. Okay. So let's pretend that, okay, and this is my 3D model, diba? My chlorine is this red functional group. Carbon 1 is this black carbon here in the center. And then carbon 2 is this yellow atom there. If chlorine, carbon 1, carbon 2, what do you notice about how its hydrogens are oriented? What do you notice? Are they on the same plane as the carbons and the chlorine? No, right? They are pointing. One hydrogen is going out towards you, into the camera, and out of your screen, and one hydrogen here is in the back going towards me, so further into your screen. How do we translate that on just pen and paper? How do we translate that going towards you and away from you? And drawing our structures. Anyone? Jamie? You have an idea? The triangles po, the dashed lines. Yes, the dash and the wedge conventions. Is that what you mean, Jamie? The thick triangle and the, yes, they're called the dash and the wedge. Officially, ha? But yes, you correct. You got it right. So tama. So notice, okay, you'll have one hydrogen. So ganyan siya. Going down, right? Going down, but towards you. And the other hydrogen going down, but away from you. Okay? And you can do the same thing. So that's carbon 1. You can do the same thing for carbon 2. Now, question. Now, the point of this is so that everything becomes a tetrahedral. All of it is just to reflect that each of these carbons are sp3. So question. Can I do this for my hydrogens here? Can I also make them go downwards like that? Is this how a tetrahedral looks like? Can I do that? Hindi, diba? So when you're drawing your dashes and wedges, make sure you orient them properly to reflect the shape of a tetrahedral. Okay, always make sure, because if you do it wrong, you do your human projection, your human projection will be super wrong, super dumb. No, not super dumb, but like, yeah, make sure that when you add your dashes and wedges, that you can recreate somehow in a different orientation your tetrahedral carbon. So no, okay, the hydrogens will not go in those positions, they will go in these positions. Okay. It should be going upwards, dash and wedge. Okay. So with that, it now becomes a lot easier to visualize. Okay, and sight along and draw our Newman projection. So now we sight along the required carbons. We're asked to look from 1 to 2. So where do we position ourselves? We have to position ourselves here. Diba? And we will, oh my goodness, what happened? We will look in this direction. So carbon 1, guys, ano ulit siya? How do we translate this now? In fact, no. In fact, since I've allowed annotation for everyone, in fact, can you guys draw the Newman projection? So carbon 1 should be a dot. Okay, and carbon 2. Carbon 2 should be a circle. There. Oh, kayo na bahala for everything else. Okay. So going up, chlorine. Tama. Okay. Okay na. Okay. We're good. Excellent. Perfect. So vertically up, the first thing I saw was people put that line up there. That represents this one for chlorine. Okay. Oops. Tama. So there's a chlorine up here. Okay. And then to the right and to the left, but going downwards, everyone put also from this central dot, these hydrogens. Correct. And then on the carbon to the back, so that hollow circle, the large hollow circle, next thing I saw was also go vertically down, someone immediately put the CH3, which represents carbon number 3, right? It's correct. And then going upwards are these two hydrogens encircled there. Upwards to the right and upwards to the left. Now, the two largest groups. Okay, so on carbon 1, the largest group is the chlorine. And then carbon 2, the largest group is carbon 3, that's CH3. This particular form, what do we call this conformation? What's the name of this conformation? A specific name, huh? This is the anti-staggered. Okay, and does it fulfill one of the requirements for this problem to draw the least stable and the most stable? It does, right? It fulfills the most stable conformation. Okay. Oops. Now, once you have that, so let's just redraw your answer. We had our chlorine there. This was everyone's first answer, no? Okay, this is the anti-staggered. So we drew the most stable. What about the next question? Or the next part? Draw the least stable form. So once you come up with your first Newman projection, translating between the other Newman projections is very easy. Okay, so once you've drawn your first one, drawing the others is easy. So all you need to do, so let's pretend ito yon. This is the chlorine in red, and then this is the CH3 in blue below. All you need to do is to pick one carbon, either the front or the back, and you pick, once you've picked either the front or the back, you will then rotate that and only that. So kunwari ako, I want to keep the back the same. So I'll keep my CH3 pointing downwards. I can then independently rotate the front. And I can find the best, the most stable or the least stable form. Or conversely, I can keep the front carbon exactly still, and then I can opt to rotate the back carbon. Is that clear? Kaya? So with that, let's translate or let's rotate our bonds. Maybe let's rotate the back. Rotate back C. So that's carbon 2. So let's rotate the back carbon. And can you all rotate it enough to create the least stable conformation and then draw it here? So I want you to do it. So this is carbon 1, carbon 2. So what would be the least stable? So the front should remain the same. Okay, tama. Okay, how about the back? What would the back carbon look like now? Tama. Everything's perfectly aligned. And what do we call this conformation of our 1-chloropropane? exactly. This is now the sin eclipsed conformation. Okay. Perfect. Great job, everyone. Okay, let's just get my mouse back. Clear all drawings. Okay, there we go. So again, first step, translate the name into a skeletal structure. Second step, try to visualize that flat skeletal structure into 3 dimensions by converting it into the dash wedge format or the dash wedge way of drawing structures. No? Recall that again, an sp3 carbon or tetrahedral carbon is 2 solid lines, 1-1 wedge, and that you have to make sure that it does reflect or look like a tetrahedral carbon. So you can't put everything on the same side, diba? Kasi you get your 3D structure wrong, everything else will not follow. So make sure you get to visualize the tetrahedralness of each of those central carbons. Next, so once you have that, consider now the sight line that's asked from you, or the perspective that's asked from you. So in this particular problem, you're asked to look at it from carbon 1 to 2. So the front should be your dot, the back should be your circle. And then you add the particular branches from each of those central carbons accordingly. And then for analyzing the conformations, you'll then rotate either the front or just the back 60 degrees at a time, no? And you create all of these different conformations. I tend to put my personal preferences. I like to box or encircle the bulkiest groups so that I know if I have a particular special form like an anti-staggered or a gauche staggered or a syneclipsed. Because once I have all of these drawings, I can then pick the most stable, like the anti-staggered, or the least stable, like the syneclipsed, or the second least stable, which would be the gauche staggered, etc. So that's what the problems will typically ask of you. Okay? Kaya? So you might ask, sir, why are we doing this? Why are we trying to visualize the different forms of a certain molecule with bond rotations? Now, when you go into biochemistry, you'll learn about proteins as one of the major building blocks of life, diba? And proteins will have a lot of these amino acids in long chains. And the amino acids are linked together by a system of pi bonds and sigma bonds. And in the parts where the amino acids are bonded together with sigma bonds, the amino acids can actually be oriented in different angles. So you can imagine different acids at different angles from each other. And it's these dihedral angles of their Newman projections that can help determine how the amino acids are folded. And remember, in protein, the shape of a protein can give it its function and characteristics. Diba? Case in point, the antigens, diba? Antibodies and antigens. So like the antibodies will be able to go and clasp onto the different antigens depending on how the receptors are shaped to where whatever. Where the coronavirus and its spike proteins will have different antibodies for that will conform to the 3D shape of that specific spike protein of the coronavirus. So understanding how to analyze on a per bond basis the geometry of a molecule will help us understand in the future when you go to biochem the bigger geometry of a more complex system like a protein. Okay? So yeah. At this point, are there any questions about our Newman projections and our conformers? Wala. Okay, and I think we have like 5 more minutes left. I'd like to introduce na lang din another topic just so that we can save some time in the next session. Okay. Here we go. Our next topic is all about another set of stereoisomers, which arise from another form of carbon. So not all of our molecules will be open chain molecules. In reality, we can have carbons arranged in rings, and these are called your cyclic systems. And if it's just an alkane, meaning there are no other functional groups present on the ring, these are called cycloalkanes. So walang double bond within the ring, walang triple bond within the ring. It's just all carbons singly bonded to each other to form a ring. So you'd have a cyclopropane system like this, for instance, 3 carbons in a ring. You can have cyclobutane, pentane, or cyclohexane. And then the rings can go bigger than that. Cyclooctane, cyclononane, cyclodecane. Chlorophyll, for instance, in the center has a huge cyclic structure. So yon. Cyclic structures are important in nature. Naming, you can go ahead and study this part on your own. Now, here's the thing though. When we took up our last lesson on human projections, we were analyzing, or this came about because, again, we said that sigma bonds can freely rotate, and therefore you can have different conformations for a given molecule. But ultimately, all of these, so the anti-staggered, the syneclipsed, the Gauss-staggered, whatever, they all represent the same molecule. We did not have to break any bonds, about to interconvert between them. We just rotated it freely. Here's the thing though, with cyclic systems, because the carbons are arranged in a ring, it hinders or it locks them in place. We might be able to jiggle them a little bit depending on how big the ring is, but ultimately we will limit the free rotation of each of these sigma bonds. In fact, for cyclopropane, which is this 3-membered ring, the carbons can't rotate at all. The carbons are solid. They can maybe jiggle, but barely. Okay? Larger rings will be able to wiggle and jiggle, but again, no full rotation, no 360-degree freedom of rotation. And because of that, you end up with groups that are particularly or permanently stuck in certain positions with respect to the ring. And this is where another form of stereoisomerism goes into play, which we call the cis-trans stereoisomerism. So remember in our last session, we took up enantiomerism, the R and the S as being non-superimposable mirror images. And then I also told you guys to study about diastereomers, among other things. So that's one form of stereoisomerism, but this is another. These are called cis-trans isomers. And it's very, very easy to understand. If you have a cyclic system, for instance, you have 2 particular functional groups or in question. And if relative to the system, the functional groups are on the same side, this is called the cis stereoisomer. Parang cis, tabi ka sa akin, close tayo. Ganyan. Yun ang cis. Okay? You'd also have another stereoisomer like this. Okay? Now you'd have the groups opposite each other with respect to the plane of the ring. This is called the trans stereoisomer. So you have to cross the ring in order to get to the other substituent. Okay. And again, these 2 forms are not interconvertible. Unlike the anti-staggered and the syneclipsed, we cannot rotate the bond to go from one form to the other. So these are permanently and chemically different from one another. But they look very, very similar. That's why they're just stereoisomers and not constitutional isomers. Okay, so again, please note the difference between constitutional and stereoisomer. Okay. Now, before we end our session, let's just try to interpret these structures. So this molecule is called cis-1,3-dimethyl cyclobutane. Bakit? Cyclobutane means that our parent chain has 4 carbons in a ring. Diba? So 1, 2, 3, 4. 1,3-dimethyl means that there are 2 methyl groups. One is located on carbon 1 and another one is located on carbon 3. And then the last part of the name, cis. Cis means that these particular groups on the ring are both located on the same side. So in this particular drawing, they're both drawn going upwards. Clear to everyone how to interpret this name? Question, how about this molecule here? If I drew the two CH3s going down, is this the same molecule or a different molecule? It's the same, no? They're both still cis 1,3-dimethyl cyclobutane. It's as if I do that and then I just turned it around. Diba? Both up, both down. So same. So please, be open, you have to like be able to really visualize things in 3D in your head. Okay, so sometimes things are just rotated. That doesn't change the identity. We didn't break any bonds. Okay, the second one, I'll leave that for you. What does it mean to be trans 1-bromo 3-ethyl cyclopentane? So cyclopentane parent chain, 3-ethyl, carbon 3, there's an ethyl, 1, there's a bromo, so there's carbon 1, there's a bromine, trans, 1 going up, 1 going down. What if I make the bromo going down? So if I have this, if I make the bromo going down, where will the ethyl be? On carbon 3, still, dapat 3 going up. Okay. But what if I put it on carbon 2? So carbon, so this is Br, sorry. What if I put it on carbon 2? Are these stereoisomers of each other? Are these still cis trans isomers? No. Ano nang relationship nila? They both have a cyclopentane, they both have a bromine, they both have a ethyl. They're now just constitutional isomers. Exactly. Hey, good job. Hey. Again, please note that sometimes the drawings won't be given to you in 3 dimensions. So these are like semi 3D drawings. But you can see that the ring is going front and back and then the groups are up and down. Sometimes, again, you'll just be given flat drawings. And so your cue for stereochemistry will again be the dashes and wedges. So something like this, for instance, you're given the cyclopentane ring as a flat, solid line drawing, and the substituents are the ones in dashes and wedges. How would you interpret, for instance, letter A? Is this the cis isomer or the trans isomer? This is the trans. So one is going away from you, one is going towards you. So this is trans. And then you fulfill the rest of the name. How about letter B? The two main groups or the chlorines, they're both on a dashed position or a broken line position. So this is the cis isomer. How would you finish the name? You just have to get the parent chain. So for instance, this is a cyclopentane. This is a cyclohexane. You'll name the branches. Okay. This is a methyl. This is a methyl. This is a chloro. Chloro. Then you have to number everything properly. There are rules for that. So this becomes a trans 1 dimethyl no space, pentane. This is one word. Okay? Sige, I think medyo overtime na tayo. Tama, sorry. At least we've gotten this far. In our next session, we'll have a problem set. So I'll be posting it later. So the problem set will cover everything from optical isomers, enantiomerism, chiral centers, R&S, all of that, to yun nga, tong Newman projections, the anti-staggered, whatever, all of that, and until this topic of cis-trans isomers and cyclic systems, and also cyclohexane systems. So there's an entire chapter that focuses on just cyclohexane systems, because cyclohexane systems are very, very important in nature, and they have their own very special characteristics. And so I need you all to study that and prepare by answering the problems that I'll be posting later. And then by Wednesday, we'll be answering and going over your answers on that as well. Okay? So yun. If you have no other questions, thank you so much for your time. And thank you for your participation, no, lalo na for everyone who drew on the board, stuff like that. So that's great. Great job. If you have no other questions, feel free to leave. If you do, I'll be the last one to leave to entertain last minute stuff. Okay? Sige. See you all and have a great rest of your Monday.
Thank you, sir.
Thank you po.
Thank you again, sir.
Sir, pwede po mag-clarify lang.
Wala.
About po dun sa cis-trans, paano ko po malalaman kung pwede siyang maging cis-trans or pag-constitutional isomer lang?
Remember that it's always a relationship. So, ang isomer, so malalaman natin ang isomer nito, dapat ganun din yung pagka-bond. So, kailangan carbon 1 at carbon 3 din. Okay, so 1, 2. So, kailangan 3. So, kunyari dito, sabi natin ito yung trans. Yung kanyang isomer dapat ganun din. Carbon 1 may CH3. Si carbon 2 may CH3. Pero ngayon, same side sila.
Okay po. About relationship pala.
Relationship siya. So,
Okay.
ito, tawag dito, cis-trans isomers. Cis-trans isomers.
Pero pag naming lang po, pwedeng maglagay ng kahit ng cis-trans dun sa isomer.
Pag meron siyang pagka-cis or pagka-trans.
Okay po. Okay.
Or minsan, kapag R and S, kailangan maglalagay ka ng pagka-R or pagka-S sa name.
Okay, sir.
Kung yung question, what's the relationship of this molecule to kunwari, this molecule of, I put the two CH3s on the same carbon. So same yung atoms, pero iba na yung pagka-bond. Ano yung relationship nitong dalawa?
Constitutional isomer.
Isomer na sila.
Okay, sir. Gets po. Thank you.
The question is always, ano yung relationship ng dalawa or tatlong molecule?
Okay po. Thank you, sir.
Okay.
Sir, pwede ko po tanungin. Medyo hindi po siya related sa lesson today. But in terms, i-clarify ko lang po in terms of the scavenger hunt. Yung reference po, may specific citation po ba na need? For example, APA. Or pwede pong, kasi nakalimutan ko po nalagay ko lang yung links mismo ng sources.
Lang. Kung kumuha kayo sa, kunyari, dun sa compoundchem.com, nahanap mo yung particular substance kung saan siya. O de yun, i-link mo lang yung website. Hindi naman siya formal paper. I just wanna make sure that hindi kayo nagkopyahan or whatever. So yun lang yun.
Okay. So okay lang, sir, yung website link po.
Okay lang yun. Basta.
Maraming salamat, sir. Have a good week po.
It's just a very simple activity. It's like light bonus. It's not even, it doesn't even give you as much points as you want. It's really just for fun. Okay.
Yes, sir. Thank you po.
Okay.
Hi, sir. I just have a question. Is the quiz that's due today, it says that it's a practice quiz. So does that mean it's recorded or it's not?
Practice quizzes, the end of module quizzes. They mean the same thing. They're practice for your midterms.
Oh, okay. So that's the 15% that's in the
Mhm.
in the okay. All right. Yeah, that's it, sir. Thank you, sir.